This course will describe the system of units used to measure electrical parameters, the relationship between these electrical parameters, and then demonstrate how to solve basic electrical problems. These are the objectives for this course. Electrical units of measurement are based on the International System, or SI, of units, previously known as the metric system. This table shows the units of electrical measurement in the SI system. Become familiar with these units and what each one measures before proceeding with this e-learning module, since these units are used throughout electrical science. The SI unit system is the only system of units for electricity. Therefore, since there is no English system of units, conversion factors and confusion between English and SI measurement is prevented. Voltage, electromotive force, that is, EMF, or potential difference, is described as the pressure or force that causes electrons to move in a conductor. In electrical formulas and equations, voltage is symbolized with a capital E, or sometimes in texts as a V. Electron current, or flow, is described as the movement of free electrons through a conductor. Current is caused by voltage. If there is no voltage, electrons will not flow and there will not be any current. Voltage must be present for current to exist. In electrical formulas, current is symbolized with a capital I. It is common to use a capital A as the abbreviation for amps or amperage. Now that we have discussed the concepts of voltage and current, we are ready to discuss a third key concept called resistance. Resistance is defined as the opposition to current flow. The amount of opposition to current flow produced by a material depends upon the amount of available free electrons the material contains and the types of obstacles the electrons encounter as they attempt to move through the material. Resistance depends on the type of material that the current is flowing through. Resistance does not change when current changes. Resistance is measured in ohms and is represented by the symbol R in equations. 1 ohm is defined as that amount of resistance that will limit the current in a conductor to 1 ampere when the potential difference or voltage applied to the conductor is 1 volt. The shorthand notation for ohm is the capital Greek letter omega. If a voltage is applied to a conductor, current will flow. The amount of current flow depends upon the resistance of the conductor. The lower the resistance, the higher the current flow for a given amount of voltage. And the higher the resistance, the lower the current flow for a given amount of voltage. In 1827, George Simon Ohm discovered that there was a definite relationship between voltage, current, and resistance in an electrical circuit. Ohm's law defines this relationship and can be stated in 3 ways. 1. Applied voltage equals circuit current times the circuit resistance. 2. Current is equal to the applied voltage divided by the circuit resistance. And 3. Resistance of a circuit is equal to the applied voltage divided by the circuit current, where E equals the voltage measured in volts, or V, I equals the current measured in amps, or A, and R equals the resistance measured in ohms. The mathematical equations for each relationship are shown on this slide. These 3 equations represent the same relationship between current, voltage, and resistance, since the second and third equations use the laws of algebra to rearrange the first equation. If any 2 of the values in Ohm's law are known, the third value can be calculated using one of the 3 formulas. The mathematical relationship can also be shown as a circle divided and labeled as shown on this slide. To find the Ohm's law formula for voltage, current, or resistance, cover the unknown in the circle, and the remaining expression will be the formula for calculating the unknown. Now, let's go through a few examples using Ohm's law to solve electrical circuit problems. For this example, find the circuit resistance for an electrical circuit which has an applied voltage of 12 volts and a current flow of 2 amps. Select the proper formula to solve this problem. Since the electrical circuit's applied voltage and current flow are known, using the Ohm's law formula for resistance is correct. Insert the known values with their applicable units of measurement in the formula as shown. Compute the value of the circuit resistance, and insert that value in the space provided, being sure to include the appropriate unit of measurement. In this example, find the circuit current for an electrical circuit which has an applied voltage of 240 volts and a circuit resistance of 80 ohms. Select the proper formula to solve this problem. Since the electrical circuit's applied voltage and resistance are known, using the Ohm's law formula for current is correct. Insert the known values, with their applicable units of measurement, in the formula as shown. Compute the value of the circuit current, being sure to include the appropriate unit of measurement. For the third example, find the applied voltage for an electrical circuit which has a circuit current of 0.5 amps and a circuit resistance of 100 ohms. Select the proper formula to solve this problem. Since the electrical circuit's current and resistance are known, using the Ohm's law formula for voltage is correct. Insert the known values with their applicable units of measurement in the formula as shown. Compute the value of the applied voltage, being sure to include the appropriate unit of measurement. Electricity is generally used to do some sort of work, such as turning a motor or generating heat. Specifically, power is the rate at which work is done or the rate at which heat is generated. The unit commonly used to specify electrical power is the watt and is abbreviated with the capital letter W. In equations, you will find power abbreviated with the capital letter P. Power is also described as the current, or I, in a circuit times the voltage, or E, across the circuit, as shown in this equation. We can also use a circle, similar to that used for Ohm's law, to obtain other values. For example, to find the circuit current, covering the I leaves the expression P over E visible. This shows that I equals P divided by E, or commonly stated, I equals P over E. Likewise, to find the applied voltage, covering the E leaves the expression P over I visible, which shows that E equals P divided by I, or, commonly stated, E equals P over I. Using Ohm's law and algebra substitution laws, we can create additional equations to determine electrical power. When you substitute the E in the power equation with Ohm's law, E equals I times R, you end up with power being described as the current in a circuit squared times the resistance of the circuit as shown in the equation P equals I squared times R. Likewise, when you substitute the I in the power equation with I equals E divided by R, you end up with power being described as the applied voltage squared divided by the circuit resistance as shown in the equation P equals E squared divided by R. Power multiplied by time is equal to energy produced or used. Electrical power in watts multiplied by time, that is, seconds, minutes, or hours, is a unit of electrical energy. Home electrical energy meters provided by a utility are calibrated in kilowatt hours.